I can start it here actually. Okay. All right, welcome everyone. I'm glad that so many people made it, even though there's a lot of snow outside, and I imagine we'll have quite a few people online. What we're going to talk about today is functional programming, and it sounds quite simple, right? I know how to use a function in Python. This should be a quick lesson, but it's actually a pretty deep topic. And I think as far as conceptual complexity, we're probably going to peak today. It's going to be a little more complicated than last time, I think, and then testing will get simpler, documentation simpler. So after today, we're kind of on the downhill slope. As way of administration, though, before we get into this, some people have asked me, like, do I need to complete all the assignments exactly on time, or when should I implement the feedback that you're providing in the pull requests? And I know this isn't like a real course and you're getting busy with other things and all that. So I'm going to be pretty lenient and flexible. Like if you want to just have everything completed by a little bit after the semester ends, including the project, then you'll still pass the class. I'll give you your certificate and you get the textbook that the department will buy you. So it's flexible, but do try to stay up on it because that just makes it easier for me to grade. Any questions about that or about how the class is going? Yeah.
I'm available.
Okay. All right, we'll talk after.
You're available, right?
Yeah, I'm available. Yep. Okay. Wonder if we can make this not show up on my screen. So Control Shift Alt H. Okay. And then F for full screen here. Perfect. Okay, so a few different programming paradigms. If you look at this, like the Wikipedia article on programming paradigms, there's like 1,000 of them. There's a bunch of different taxonomies. So I've kind of struggled to narrow it down to just these three, but I think this is good enough for our purposes. So the first one is procedural. And in procedural programs, you're basically describing what should happen kind of line by line. Do this, do that, and so on. And these are really good if you need to be close to the hardware. For example, if you're trying to operate in some kind of constrained environment, or if you're writing an operating system, this is a good paradigm because, again, it's close to the hardware. We also have object-oriented programming. And how this works is, we saw last week, we encapsulate state and behavior in kind of one abstraction known as an object. And so if you have complexity related to how data should be generated or changed, then this sort of helps you manage that complexity by encapsulating it. What we're going to talk about today, though, is functional programming, and this is a different paradigm. Our abstractions in functional programming are going to actually be much closer to mathematics. So we want our programs to behave, our functions to behave like proper mathematical functions, and we'll get into what that means in a second. But I think this paradigm is really good for data processing, parallel computing, and science in general, where we're working closely with some kind of equations, or we can model what we're doing as a processing pipe flow, processing pipeline, or functional composition. So neither of these, or none of these three, is better than the other. They have different strengths and weaknesses, and then realizing, which one to use and when, I think, is just a skill that you develop as you do more and more practice as programmers. All right, so functional concepts, we can't get into pure functional programming. You'd need a language such as Haskell, and I'll mention Haskell and how it does things throughout this presentation. But we're just going to talk about a few concepts related to functional programming. And the first one are these related concepts of pure functions, immutability, and side effects. Then we'll talk about how Python handles scope and higher order functions. A higher order function is just a function that takes a function and returns a function. So think functional composition. We'll talk about anonymous functions, two building blocks, map and reduce, and then finally recursion. And if we have time, I also want to cover two important Python concepts that aren't particularly functional, but you'll see them everywhere, and this is kind of the best place they fit in the course. So the first one would be generators and then context managers. Okay, so to motivate our discussion on functional purity, let's define three functions. The first one is Eileen's favorite function. This is AXB. And what it does is it takes a scalar and two vectors, and then it's going to multiply the first vector by the scalar and then add the two vectors together. This one is just a vector element-wise divide. That's what that symbol means. And then this one is an element-wise raised to a power. Okay, so we have these three. In a purely mathematical sense, if we change the order of these, shuffle them around every which way, does it really change the meaning in any way?
Sorry.
Yeah.
People were asking to see what link they can use to join online.
What link?
Yeah.
It's in the student discussion board, that link at the top. Who's asking?
Wait up.
Can you someone can just email them the link real quick? Okay, all right. So it doesn't matter if we change the order. So let's implement this in Python now. So we have our three functions, funcF, funcG, and funcH. So those are going to be corresponding to these three functions here. But I'm not going to fill in the implementation yet. We'll see why in a second. So we'll import NumPy. We're going to define a random vector and then a vector full of ones. And then our A is just going to be a scalar of 12. So if we perform these operations in this particular order, the question is, does F1 equal F2? And so if you see up here in line 1, F1 is just calling funcF with A, X, and Y. And then F2 is the same thing, A, X, and Y. It's just in line 7. What do you think?
Same thing. It should be the same. We should modify the AX or Y. H to G from the previous. Can you just go to the previous slide?
This one?
Is the np.random 10 creates different random numbers every time you call
It does, but we're not calling that more than once. We have the same X once we create it, right?
Okay.
So this is the same X here every time. Okay, so you're hitting on it exactly. So if we want to assert that this is true, it actually depends on functional purity, depends how we implement these functions. So let's look at the example that you're suggesting here. These are pure functions. So we have an input and an output, and the output depends solely on the inputs, and it doesn't cause any side effects. Exactly, that would be a side effect. So if we implement them in an impure way, then what we're actually doing is overriding the first array and returning it. So this is causing a side effect that will propagate downstream and make that nice mathematical property that we're hoping our functions have not hold any longer.
So what if we like assign a different variable to what we return? Does that make a
So here,
no with the impure function?
so the trick is with this bracket colon, it's saying overwrite the values of this array with whatever I give you. So we're modifying them in place. What we're doing here is we're actually allocating a new chunk of memory for the array, which we call out, and then we're returning that.
Jin's got his hand raised online.
Okay, yeah, go ahead.
Yeah, so
Go ahead, Jin.
Yeah, just a quick question. If you go to impure functions and if you
I don't know if we can hear him.
You might have to turn the sound up here as well.
Oh,
Okay, 1 second here. It looks like it's up all the way. Oh, it might be because I'm plugged into this camera.
Yeah.
okay, no.
All right, I can go ahead and.
Just. We have something in the chat. Oh, he's going to type it. Do you want to just read his question? Okay, let me keep going for a second, and we'll circle back to that once the question is out. Okay, so the important thing here, yeah.
But it isn't the scope of the variable within the function? How does that happen?
Okay, so you're thinking because
Yeah.
this here, you think that this might be a different X than the one you pass in. Is that what you're saying?
Yeah.
That's how it works in C, because C is pass by value. Python is a pass by reference language. So it's almost like using a pointer here.
So like with Python, you can modify your variable. components need to do that, you have to force it like point your reference to that
Oh,
variable. And it looks like Jen's function, or Jen's question may be very similar to the impure function. If you have x equal a times x, does that change outside the scope?
X equals a times x. No, so that wouldn't change it. It will bind a new variable called x.
And then the other question is, if you remove that square bracket colon, does that change the results at all?
Yes, so that would be the case where we're binding a new variable called x that will squash the old one. And so we're not actually changing the memory in place.
So here when we're calling x within the function, when is it like it's modifying the global x variable or is it?
That's right. So it's not modifying a new one. It's saying take all the values of x and overwrite them.
So yeah, we can modify the global variables within function like that.
If they're mutable variables, and we'll get to that in a moment. Yeah. There is a way to make arrays immutable. That's kind of in the weeds, so we'll talk later if you want to talk about that. Okay, so the important thing is that it doesn't have anything to do with correctness, whether a function is pure or impure. Both pure and impure functions can create the correct output. So if you just look at the inputs and the outputs for one of these functions independently, they're both producing a result you'd expect, right? But the difference is that pure functions are going to behave more like mathematical functions. And what I mean by that is that their outputs depend exclusively on their inputs. They don't cause any side effects, so we just showed a side effect here. And they are referentially transparent. And that's a fancy way of saying that at any point in the program, you could actually replace the function call with its value and it wouldn't change the behavior of the program.
How common are impure functions?
Have you ever put a print statement in your function? That's
No.
impure. No, I'm not saying there are some side effects that are obviously more dangerous than others. A print statement isn't going to cause the things we're looking at here, but yeah, so they're very, very common. Pure functions, though, are much easier to parallelize because you know exactly what the inputs and the outputs should be. There's no side effects. So you essentially just have to look at a dependency graph of what inputs each function needs, and then you can figure out relatively easily with like a DAG which branches can be parallelized. But they are restrictive, right? We saw that there's some things that we can't do that maybe it would make sense to do in some contexts. So we're kind of trading off. We're going to give up some freedom of how we use our functions in order to have these nice mathematical properties. And I'll argue it makes it easier to debug. So I'll get into a case for this later. Let's just check if we understand this idea of pure functions. So this function, is this a pure function or impure? Lines 3 through 4.
Pure.
Okay, why do you think pure?
It's returning but not assigning value to the, let's say A.
Yeah.
Returning the value, but it's not assigning it to A.
Okay, so you're right, it's not causing side effects. That's an important part. But the other thing we're looking at is that they depend exclusively on their inputs to form their outputs. Right, so in this case, we're looking at this global state, which could change out from under us at any time. So this is an impure function. What about add 2? That's as pure as it gets, right? It's only adding 1. Yeah, but hey, style was 2 weeks ago. We're done with that. Okay, now we have add 3. And we just talked about this. It's causing a side effect because we're printing something to standard out. So if we replace this function with its output, it wouldn't print anything. So it's not referentially transparent. It's not a pure function. It's a benign side effect, but it's a side effect nonetheless. Okay, what about these ones? So this one has some mutable state, some dictionary it's going to create, and then it's going to start changing it. So what do you think? Is this pure or impure? Okay, why do you say that?
Because 2 is not modified as up here.
Right, and it's not depending on anything besides its inputs. So if you think of it within its own memory space, it doesn't have any external dependencies. So yeah, it's fine. It's fine to have that memory that only it controls, and then it can change it. It's still a pure function. Okay, this one I put in, this is a bit of a trick question. This is actually impure, and this is a gotcha you might run into. So when you assign a default value to a function, like I'm doing here with sum list equals 1, 2, 3, that is actually shared every time you call the function. So if you modify it in a function call, next time you call the function, it won't be 1, 2, 3 anymore. It'll be something different. So just keep that in mind. Okay, so that's functional purity. Another related functional concept is immutability. So we have two sequences that are built-in types in Python that are used all the time. So we have list1 and tuple1. Okay, so list1, if we want to change a value, sure, no problem. List2, if we try to do this, it's going to raise an exception. So the difference between these data types is just that the tuple is immutable and the list isn't. So when I first encountered this, I thought, well, I'm never going to use a tuple. This just seems like a better version of it because I can change it, right? Why would you think that Python has both of these data structures?
Yeah, some instances where we don't want to make a list mutable.
We want to guarantee that it won't change, right? Yeah, exactly. So
Then data, you call it your list. Something that
yeah,
Exactly.
yeah. If your program depends on this not changing, you might want to enforce it with an immutable construct like this. So the last question then, why would we limit ourselves as developers? Like, I'm writing the program, I know what I'm doing. Why would I limit myself in this way?
It has to do that you need to keep track of.
Yeah,
It might, like, when you know you're gonna pass off to somebody else and don't really trust them to not make a mistake.
right. Like if you're writing a library, for example. Good. That's true. A lot of times when I'm programming, especially when you start getting threads and other concurrency involved, I kind of feel like this. So having these immutable variables kind of keeps this from getting too tangled. And in fact, here's a quote I like: all race conditions, deadlock conditions, concurrent update problems are due to mutable variables. So there's this whole class of bugs that are extremely difficult to solve that just go away if you don't use mutable state. Sounds pretty nice, right? Okay, so what we talked about, and this was a slide kind of for Jin, we talked about this last week a little bit, but can we mix the benefits of some of these functionally pure immutable state ideas with object-oriented programming, or is it purely a functional thing? And I think we can mix it fairly well. It takes a little bit of discipline, but I think we can do it. So what we're doing here is we have a function that takes an instance, and in this case, we'll just think of the instance as the namespace. Remember, it's like a dictionary, but we access it with a dot instead of brackets. And then we're gonna double the state, whatever state variable is, and then we're gonna return a new instance. So if we just set up a class that does that, and then bind this as a method. So essentially what we'll be able to do, just like we talked last time, we have line 11, which says self equals 1. So we create a new instance. And then these two things are exactly equivalent, right? So just because it's a method on a class doesn't mean that it can't be functionally pure and have some of these benefits. Now you can't really make it immutable very easily, but as long as your methods are returning new methods and not changing the state in place, you get some of these benefits. So Jen, to answer your question, that's part of the motivation for making some of the design decisions I did in DASCOR. Hopefully that provides some more context for that.
This line 11 is supposed to be class.
Yes, yep. Yeah, thank you. Yeah, I'll fix that. And this one looks like it failed. Okay. So what's going on here is I'm just showing you how you can use a data class. We talked about that last time. And you just have this little @ data class. If you do open paren frozen equals true, then now you have an immutable data class. So that's an easy way to get It's not truly immutable. Like if you dig under the covers enough, you can figure out a way to change the state, but you're kind of marking it as, hey, don't change this. If you do, you're kind of on your own. So that's an easy immutable construct to get to. Okay, so in a couple of sections, I want to just look at this idea of how different libraries handle shared mutable state. And this is an example from scikit-learn. So when you create an estimator in scikit-learn, in this case, we're going to have this k-means clustering thing. I can't remember exactly what it's called, but essentially you give it some parameters that won't change. And then when you fit it, it has certain parameters that do change, like its labels and its cluster centers. And so the way that they sort of put some guardrails around this shared mutable state that can be a little bit dangerous is they have this trailing underscore to indicate, hey, this is going to change in the class potentially every time you call fit. Okay, so that's one approach. It's not a pure functional approach, but it's a way to do that. Okay, so I had a pandas example, but whatever the syntax area here is probably not loading that. But the idea with pandas is that everything returns a new instance. You don't modify state in place unless you opt into that behavior. So pandas methods have an in place keyword. You would say in place equals true. So it's like, we know modifying data in place is dangerous. So we're going to do the safe thing by default. If you really need it, then you can opt into it. And I think that's a pretty sensible approach to this as well. Okay, so just to summarize immutability, like we said, objects can't change. This eliminates a whole class of side effects that can cause issues in your programs. What's kind of interesting is that the memory location no longer matters, at least for correctness, right? So if you have like a shared memory location or distributed memory, if this state can't change, it doesn't really matter where it is. If it can change, then it does matter where it is because certain processes might access it and change it. So it makes it nice in a concurrent setting. New objects are created by functions. You're never going to modify something in place, like I said. There's a few immutable data types built into Python. We also saw the data class example. And I say the bottom line, if this is maybe a little bit too much, a little off in the weeds, the thing I would say is avoid modifying data in place whenever possible. So if you can return a copy, always prefer to do that, unless you really need to modify data in place for some reason. But then you have this whole other can of complexity that you have to deal with. Okay, any questions on functional purity immutability? Hopefully you've seen what it is and why it's beneficial, even though we do limit what we can do as developers when we impose it. What's really cool, in a pure functional programming language like Haskell, it's completely lazy. And it means that you can't reason about your program going from line 1, 2, 3, 4, 5. You just sort of describe what the program should do, and then the compiler might change the order. It might combine some of the functions. And it can do that because it has these guarantees of immutability in pure functions. So just food for thought. You can do some pretty interesting things when you have these guarantees as a language. Okay, so now we're going to talk about higher order functions. So in Python, this is the term, functions are first class citizens. And that means just like an integer, a equals 10, we could have def. Both of these, so func and a, can be input parameters to another function. Okay, so here's an example. Function 1 is just going to print something. Function 2 is going to take a function as an input and call it. And so what's going to happen when we execute line 7? Yeah, exactly. So function 2 gets function 1 as its input, it calls it, and then that print happens. What can get confusing though is Python's scope. So if you reference a variable inside of a function that's not one of its input parameters, then which function or which variable is it actually referencing? So here's the rules, and then we'll go through a few examples. So it's called LEGB, how scope works. First, the function is going to look locally. So whatever's in its own namespace. If it doesn't find the variable it's looking for there, then it's going to go to the enclosing function if it has one. And then finally global state and then built-ins. So let's look at some examples here. So we have our function 1, and then we have a nested function, function 2. And what function 1 returns is the output of function 2. So in this case, function 2 gets called by function 1, right? And what will be the value of arg here? So we have 3 args, right? We have one that's in its local namespace. We have one that's in an enclosing function namespace, and then we have a global one. They're all named the same thing. So which one is it going to return?
1, 0.
You said 2? 2.
It's 2.
Yeah, 2. Right. So if we go back to this, we start with the local, then we look at the enclosing function, global, and then finally built-ins. So it returns 2. What if we take that one away? Yep. And if we take that one away? 0. You got it. Yeah. So scope, is that fairly clear how it works? I think it's pretty sensible, but it can get a little bit confusing. Yeah.
Are there any ways to force Python to limit its scope more? Like if you only wanted to look at 2 levels, then give up, so that if you reference a variable that just doesn't exist, you're not wasting much time.
So you would say never go to the global scope, for example? I've never seen it either. I don't think so. But yeah, I'll look into it. Okay.
It wouldn't be possible to call function 2 if you weren't already in function 1. Is that correct? So that if I wanted to call function 2 on line 11.
Okay, so let's imagine function 2 is actually above function 1, and then you want function 1 to call function 2. It would be possible. Yeah, it doesn't have to be nested because it. No, it would be, in this case, it would be exactly the same. And the reason is because function 1 is going to search its local namespace for something called function 2. It's just following the same scope rules. It's going to say it doesn't have it. It doesn't have an enclosing function, so it's going to go to the global namespace, which would have function 2. But function 2 scope is going to be different if it's nested versus not nested. So yeah, we'll see that in a second. Okay. Here's an example. Okay, this might get confusing. So this is kind of what you were talking about, right? What is this going to return? So let's look closely. We have function 2. It takes a function as its input. It defines this arg2, and then it calls that function. Now function 1 here is just going to have arg. So we're not sure where it's going to get that argument from. So we need to figure out how the scope will work. And you have 2 guesses here. It's 1 or 2, right?
Well, it calls function 1 first, so it's still going to be returning 1. And then it goes in the input of 2, which doesn't actually care about arg, even though it modifies it. So it'll be 1.
It will be 1. Yeah, and the simpler way to think of that is that basically the scope lookup rules are applied where the function is defined, not where it's called. Okay, you can, so related to your question, Eileen, but not exactly the same. If you want to tell this, don't look at arg in this scope here, but actually use the global one. There is a global keyword you can use. And so in this case, it would return 0. And there's also a non-local keyword, and that will say, look at the scope above this one. So the nearest scope above the current scope. Okay. The thing to note though here is you probably don't want to use global or non-local. Usually it's a bad idea. So forget that I taught you that. Okay, decorators. So finally we're getting to something interesting now that we understand scope. This is used all the time in Python. So what we have going on here, we have a function, just like the other functions we're looking at. It takes a function as an input. And then there's an inner function, which is going to have some arguments. and then it's going to return the inner function, not the input function. So for example, this inner function is going to modify some input arguments. It has the same arguments as add. And then it's going to call the function that was given to the outer function. All right, is anyone following? It sounds confusing as I'm explaining it. Okay, so the idea then, we say add is equal to a decorator. We give it that input as the add function. Now what's going to happen is decorator is going to return wrapper. So it's going to return that nested function, which will actually call add when it gets called, but it's going to first modify the input variables. All right, any questions? Yes, yes. Maybe there's a way to explain this in a different way. Okay, let's look at this again. So what does this function return called decorator? That's right. And then let's just look at the wrapper function. What is it doing? Two args. And then it calls this new function, func, but where's it getting that from?
That's gonna be our add function.
It's going to be the add function, but yeah, it's getting whatever is passed to this decorator function. So that's where it's finding it.
So require the functions.
Yeah, exactly.
So is our output in your
Yes. Yep. Outputs for, you got it. Okay. So the decorators are a way to modify a function by giving it as an input to another function, or a higher order function, as we call them. So there's some nice syntactic sugar in Python. So take a look at line 11, add equals decorator, open paren add. So we're overwriting the add name, and we're going to actually call add wrapper because that's what's being returned. So it's going to look like it's the original add, but it's been modified. So this does exactly the same thing. This at decorator is going to just replace add with whatever decorator returns, but it's going to pass the original add as the first argument. So someone besides Eileen, when we call line 12, what's it going to return? 4. Yeah, why?
Because added the decorator calls the wrapper function, changes the R1 and R2, and then again calls the add.
Yeah, exactly. So what we're looking at as add is actually wrapper that was returned by decorator. Okay.
So, does it need to be decorated by the?
No, so this is exactly equivalent. So line 11 is doing the exact same thing as that at symbol.
Oh, okay.
So we can get rid of line 11 and add the at symbol to the top there, just like this, and that's going to be the same thing.
Okay, so we can, the greater function can be something else, and then we just use at something else.
Yeah.
Okay.
Yeah, that can be anything that accepts a function as a first parameter. It's just a special kind of operator. What else does the add symbol do in Python, or the at symbol, sorry?
How do you use the JIT compiler?
I think when you do a JIT, it's a decorator. It's the same thing. So at JIT, and yeah. So it's a newer thing. It's actually matrix multiply now. So you can do array 1 at array 2 matrix multiply. Yeah. Trivia. Okay, so let's see this point here. So you don't actually have to return a new function. A decorator could return the original function. And oh, sorry, you have a question?
Why do we do decorators?
I'm going to show you. Yeah, it's actually quite useful. I'll show you. And this is one example. So what we're doing here is we're creating a decorator that's going to add the function to some kind of registry. Maybe we want to keep track of this function for some reason. or allow the user to say, this is a special kind of function, and here's the list where I'm keeping track of these special functions that do something. So in this case, we have our global registry. We use the @decorator. It's going to get our add function, put it in this list, and then return the same add function. So unlike previously, it's not replacing it with a new function. It's the same thing. It's just done something with it before it returns it. Okay, so there's the functools module is where you find a lot of the functional features in Python. itertools is another one. But what the wraps decorator does, so if we're going to create a decorator that takes a function, we might want to transfer some of its metadata. For example, its docstring. If you write some documentation and you don't do this, then the return function, which is not the original function, won't have the same docstring, and maybe you want it to. There's a few other things like the signature, and there might be something else. But anyway, if you're actually returning a new function, it's a good idea to do this @wraps so that it transfers the metadata, so that the new function that's returned looks exactly like the old one as far as, you know, documentation, a few other things. This is particularly useful when you're using these args and quargs. Has everyone seen that? Star args? Okay. Yeah, basically what star args does is you can have a function that has star args, and then if you return star args, it's just a tuple with these sequential values you pass in. It's quargs is the same thing, star quargs, but it's for a dictionary. So you pass in 1 and 2, and then it's going to return a dictionary whose keys are 1 and 2, and the values, confusingly enough, are also 1 and 2. Okay, so if you're doing some kind of generic decorator, and this will allow your function to take any input or output, you'd use this pattern here. Okay, so why would you do this? Decorators in the wild. Let's look at some example use cases. Here's one from functools called cache. And so conceptually what cache is doing is it's basically it's creating a dictionary, and it's going to take an input, store that as a key, and the output's going to be the value. And now every time you call this function, rather than calling the function immediately, it's going to see first, has it cached the value, and then just return that rather than doing another computation. So something like the Fibonacci series here, where we don't want to keep calculating it over and over again, this is a good use for cache. Yeah.
So I think it's more efficient to use cache rather than the if loop, right? Because in that case, you can imagine, okay, if the answer is known, like the output of this function, don't do the computation. It's exactly like an if. No?
So we'll talk about this particular function when we talk a little bit about recursion. Something else is going on here as well. So this is a recursive function, meaning it calls itself. But if the value of n is, if it's 1, is that what you're saying? If it's none?
No, I mean, what? Okay, can you explain what does this function? I mean, this
@cache. Okay. So yeah, imagine that instead of doing the decorator, we just had a dictionary, and we store the input value. So we store n, and then if we don't have n in the dictionary already, we'll calculate it and then store n and its output. And so next time we call the function, rather than saying, let's just recalculate it, what we're going to do is look in the dictionary. If we have the value already stored, just return that. Don't recalculate it.
Okay, my point was you can do it with an if as well, no?
You could, yeah. But you'd have to have like that logic built in. You'd probably have like a mutable dictionary. You could do it that way, just be more complicated.
I'm not exactly understanding why there isn't else in here. So, for example, n is 1.
Okay.
Returns n and then runs fib1 2.
No, because it returns
So that's the
fib1. That's the
Oh,
end.
just takes out.
It kicks out. Yeah. Yeah. We'll get into this in the recursive part. So we'll talk through the anatomy of a recursive function in a second. Here's one in functools called partial. And so This one is useful if you want to bind a default parameter to a function. So in this case, we have add A and B, and then partial add. We're going to create a new function that has B set to 2. So now we can call our partial add with 1, and B is automatically going to be 2.
So what if we call it with one and another number? That's it.
Good question. Does it override it, or is it going to raise an exception? I don't remember. We'll have to test it later. We'll see this next week. So PyTest, the main testing framework in Python, it uses a decorator to mark a fixture. A fixture is just something that performs some setup or tear down for a test. And it just uses a simple decorator like that. So it's nice, clean syntax. It's very clear when you read it what it is, but it's doing something more complicated behind the hood, under the hood. Flask, if anyone has done some web programming, you use decorators to specify your routes. So if you went to my website / so the home page, then it's going to find this function and return whatever this function returns. So functions that take other functions are decorators. You can use that @ symbol for shorthand. These return new functions, or they don't have to, but they can return new functions. And most often what their meaning is you're marking or registering a function for something. Like how we saw this function is a fixture. We use that @ symbol pytest.fixture or app.route. So it's just a way to make it simpler to read what the function is supposed to be doing while hiding a lot of complexity of what you're actually doing with the function behind the scenes. Okay, so anonymous functions are functions that don't have a name. And so let's look at an example here. We have a list and we have a mapping. Now it would be pretty simple to sort this list. It would just be 1, 2, 3. But if we want to sort the list based on the value for the corresponding key in the other map, so we want to sort the list, but we want to use the dictionary instead, right? We can do that with an anonymous function. So in Python, the built-in function sorted takes an argument called key, and this can be a callable. So you could pass a normal function in here, or in this case, we're using an anonymous function, which we denote with lambda. And so lambda x means that it's a function that has one parameter called x, and then the colon tells us that it returns whatever's after that. Nope. Okay, so looking at the normal function equivalent of a lambda, we said func1 equals lambda x, y, z, colon, x plus y plus z. That would be exactly equivalent to lines 5 and 6. The thing though about anonymous functions is you're really only supposed to use this syntax when you're not giving it a name. So line 2, you shouldn't do it like that. You should just define function as in lines 5 and 6. Okay, how are we doing?
Yeah, 5 or 6 minutes.
Okay.
So are you saying line 2 is not correct?
No, it will work. It's just not good style. We talked about PEP 8. This is explicitly forbidden by PEP 8.
But it must work.
It'll still work fine. Okay, so map is basically like a for loop, but you're applying a function to each element in your sequence. So in this case, for mapping, we have our anonymous function, which is just going to square each element, and we're mapping that on my range. So range is 0 through 9. We're going to go through each element, square it, and then return that sequencer list. Okay, map is fairly simple. A lot of times, though, it's much more readable to use a list comprehension or a generator comprehension like I'm using here. Are you asking why it's curly bracket? There's
No, I was gonna just think a thing.
okay, yeah.
Map is exactly this way are commonly used as areas in Madagascar.
Hmm. Yeah. There's nothing specific about Python here. Yeah, this is used all over the place. Map,
This is something that
reduce.
took me a long time.
Ah.
I think that's why I was assuming the bracket, the braces this way, because it's in a map function. The lambda function is inside of it.
Yeah. So map itself is a higher order function
Yes.
because it's taking a function as input.
Sorry, is this outputting a tuple instead of a list?
Yeah, this is a generator expression, which maybe we'll talk about in 2 minutes. I don't know if we'll have time. And the reason is map is also a generator. It's not a list. Okay, I'm actually going to skip this example. So this, I'm going to highlight Gwen's homework here. This is from Gwen's style homework, and I thought it was actually a pretty cool example of functional programming. So thumbs up on that, Gwen. Basically, rand range takes a value and it returns a random integer. So if you give it 10, it will return a random integer between 0 and 9. And then repeat just repeats 10 times. And we could do something similar like this. But yeah, this is a good example of map. Reduce is kind of similar to map, but what you're doing is you're actually taking a function that has 2 inputs. You're going to apply the function here. And then this is going to be the first input to the next iteration. And it will apply the function here. Does that make sense? And then you just keep going until you have 1 value left. So you start with a sequence and you end up with a single value at the end. Accumulate is similar, but you're going to have intermediary values stored. So if you think of like a cumulative max, that's exactly what you could use accumulate for. Okay, last topic we'll cover in just 2 minutes here is recursion. So recursion is a technique where a function calls into itself. So we see our Fibonacci series here. And what you have to have is 1 base case. So there has to be a way for it to get out of its self-calling loop here. It's not a loop, but self-calling behavior. If you don't have this, essentially, it will just overflow the stack. You'll call it so much that Python says no more. Then we have some recursive cases here, and then the output. So I wanted to diagram this on the board and go more into it, but I think I have some good resources I've linked to already. So I'll refer you to those, and let's talk about it more if you're kind of confused about recursion, and everyone is confused about recursion when they first see it. Yeah. Okay, so it works really well for like parsing recursive structures. So imagine you have a tree, and then each node could be like another branch or some kind of terminating node. In the exercise, we're actually going to look at a family tree for some US presidents and ask questions about their ancestry. So that's a good use of recursion. It is easy to overflow the stack, and that happens if you go more than 1,000 levels into recursive calls. Python just cuts it off. It's just a random thing that Python sets. You can change it, but that's the value that they've set. It can be difficult to understand though, so use it sparingly. Like there are some legitimate use cases, but mainly showing off and coding interviews, I'd say, is where it's used. Okay, and we're out of time. So I'll try to cover generators and context managers in some other lecture, because I think they'll be useful for you to know about. Okay, any last minute questions? Okay, let me ask one question. Why do we care about immutability and functional purity? Hopefully take this bit away. And why is it useful in some cases?
I like the idea of being able to build those like DAGs of sort of what depends on what.
Yeah.
Especially for tools that are trying to like automate probabilism and stuff, or even when people are trying to figure out what can you port over onto GPU and what's the order of who needs to have what data at each point in time. Like that makes it really much more straightforward to do.
Exactly. Yeah. If you have pure functions, yeah, makes it simpler to look at as well. If you have pure functions, immutable data, then you can reason about it explicitly based on what the function asks for and what it outputs. If you have side effects, who knows what's going on? It gets really complicated. Okay. So next week we'll talk about testing. We'll start with an overview of just general software testing and then go into the PyTest framework. And anyone working on DAS Day, I would strongly encourage you to attend.
I have a question with shutdown first.
Okay, stop the meeting. Okay, do we have any other questions here? I think we're good. Yeah, anyone online who wants to ask a question or have a follow-up conversation, just shoot me an email. All right.
Is it okay if I encourage people in our